Now, before I proceed, I would like you to recall the following fact from linear algebra, which told you that the homogeneous system of linear equations is always consistent. Correct? Because the trivial solution is always there. And same thing can be said to homogeneous ordinary differential equations with given conditions. They are always consistent. Okay. Now in this case, when I say given conditions, I mean initial value problems. Okay, because now we are going to see that you can have some boundary value problems, second order differential equations, which may have unique solution, no solution, or infinitely many solutions. And don't be under the impression that these are general solutions. What I mean here is only particular solutions. Of course, they will have a general solution, correct? Okay, so now you'll realize that the problems that we are going to deal with now, the differential equations, they have very little to do with the general solution, but they have more to do with the particular solutions. This means, in addition to the differential equation, we will always also be given two boundary conditions, because we will be discussing only second order differential equations. Okay. So as opposed to the theorems that we saw earlier in our lecture for initial value problems, they, as long as p of x and q of x are continuous, the solution exists. And when you substitute the values, use the initial conditions, which are y of x not equal to something and y prime of x not equal to something, and so get the values of the arbitrary constants, that will be it. Okay, to find the particular solution. So now the question is how to solve boundary value problems, or is it really true that they may have a unique solution or no solution or infinitely many solutions? So to understand this better, let's take one standard differential equation and try three different possibilities. Okay. So the differential equation that I'm going to consider is a homogeneous equation of second degree linear with constant coefficients, right? You know that its general solution is c1 cos x plus c2 sin x. So this is basically the differential equation of the harmonic motion, simple harmonic motion, right? So let us suppose that these are the boundary conditions: y of 0 equal to 2, y of pi equal to 1. So I'll use the first boundary condition, which will give me 2 equal to c1 into 1 plus c2 into 0. So this gives me c1 equal to 2. And if I use the second condition, then what will I get? If I use the second condition, then I'll get 1 equal to c1 into cos pi is negative 1 plus c2 into 0. So this is giving me c1 to be negative 1. Now, is this ever possible that 2 is equal to negative 1? No, this is never possible. So this tells me that we cannot have a solution to the differential equation y double prime plus y equal to 0 in addition to the boundary conditions y of 0 equal to 2 and y of pi equal to 1. So this is no solution case. Okay, this is the no solution situation. Okay, so let's go to the second one now. Y of 0 is 2, so c1 is 2. Let's go to y of pi by 2 equal to 3. Now y of pi by 2 equal to 3 means 3 is equal to 2 into 0 because cos pi by 2 is 0 plus c2 into 1 because sin pi by 2 is 1. So this is giving me c2 equal to 3. So this is unique solution. Correct? And what is that unique solution? That unique solution is 2 cos x plus 3 sin x. Now you You'll guess that the third one has infinitely many solutions. We'll see what that is. Okay. Y of 0 is 2. So C1 is 2. And y of pi is minus 2. And if I use y of pi equal to negative 2, I'm getting the same thing. Which means negative 2 equal to C1 into minus 1. Okay, so this means that this is also giving me C1 equal to 2. That is, there is no restriction on C2. So this has infinitely many solutions. And the solutions are y equal to 2 cos x plus c sin x, where c can be any real number. Okay, do you understand this? How can a boundary value problem have no solution, unique solution, and infinitely many solutions?
Yes, sir.
Okay. So what exactly the eigenvalue mean in such a context? So I'll be considering the same differential equation and I'll be modifying it a bit. And we'll talk about 4 to 5 different boundary conditions. Okay. So you can apply this in general to any given differential equation, but we will restrict ourselves to the eigenvalue problems. Well, I have not yet defined what an eigenvalue means in the context of differential equations, but let us say that we are solving y double prime plus lambda y equal to 0. You can happily say here that the general solution is C1 cos of root lambda x, assuming that x is the independent variable, plus C2 sin root lambda x. Correct? Can I say that? Yes, I can say that. I mean, if you solve the auxiliary equation, you are going to get m as plus or minus negative of plus or minus root of negative lambda. Okay. Yeah. So we are going to deal with these 5 boundary conditions or boundary value problems, and let me tell you what all of them mean one by one. Okay, we're going to make use of these in solving partial differential equations, mind you. We will use these conditions or at least some of them in solving partial differential equations. Okay, because there you have the boundaries, right? For example, if you take a wave equation, then it has a fixed boundary. Example, consider the first one, y of 0 equal to 0 and y of l equal to 0. So the first boundary condition, what does it represent physically? Fixed ends in case of wave equation. And so on. Okay, so y dash of 0 and y dash of l equal to 0, well, it doesn't really have any physical significance as far as wave equation is concerned, because derivative of position with respect to derivative of displacement with respect to position something. I mean, if you multiply it by velocity, then you can say that it is acceleration and so on. But yes, you can consider y dash of 0 and y dash of l, y of 0, y dash of l, y dash of 0, y of l. So the boundary conditions 1, 2, 3, 4, these basically cover the function's value at the ends and at any one of the ends, and the value of the derivative of the solution of the function at any of the 2 ends. Okay, so that gives us 4 possibilities. You can see all 4 possibilities being covered. For simplicity, we are taking them to be zeros. Okay, the fifth boundary condition, okay, which is y of negative l is equal to y of l and y dash of negative l is equal to y dash of l. This is called as periodic boundary condition. All right. Cool. So we'll see certain theorems, and you can prove some of them. I'll leave that to you as exercise. Okay. So what is basically an eigenvalue here? Okay, what is basically an eigenvalue? So for first answer that question, sorry, I think I missed one slide here. Yeah. So what is the eigenvalue problem as they say in your syllabus? Given a differential equation y double prime plus lambda y equal to 0, let's call it 1, with two boundary conditions. Those values of lambda, okay, those, I'm not saying lambda squared or anything of that sort now, I'm just saying lambda here. Okay, so whenever you have a differential equation y double prime plus lambda y equal to 0, I will call those values lambda to be eigenvalues, okay, for which our differential equation has a non-trivial solution. Okay, I mean it is guaranteed to have a trivial solution 0 0, but it can also have a non-trivial solution, and whenever it has, we call it an eigenvalue. Now please remember that eigenvalue or the determination of lambda is heavily dependent on the boundary conditions, which we have discussed right now, the 5 boundary conditions, okay, which may give rise to something like no solution, unique solution, and infinitely many solutions. So we will come to that later, okay, once we see what everything gives, each of the 5 boundary conditions gives. Okay, so let me repeat. We have a differential equation y double prime plus lambda y equal to 0. You may ask, why am I not taking y double prime plus something into y prime plus that equal to 0? Well, you can change the origin and get rid of the y prime term. Okay, we'll not consider that, we'll just stick to this simple problem. Okay, I mean you can dig deeper, but this will give you the whole essence of what they mean by an eigenvalue problem. Okay, so y double prime plus lambda y equal to 0, two boundary conditions, determining those values of lambda if they exist, for which this has non-trivial solution, we will call those values to be eigenvalues, and the corresponding functions, the general solutions, these will be called as the lambda eigenfunctions. Okay, this will become clearer if whenever we see the theorems related to them. Okay, so remember the differential equation that we are solving, and what exactly are we going to call an eigenvalue? Whenever it possesses a non-trivial solution satisfying the boundary conditions, we're going to call that as the eigenvalue. Okay, you can have multiple eigenvalues. In fact, all of them, the boundary conditions that I stated, all of them do have infinitely many eigenvalues. Okay, we'll see that. Okay, so the first theorem tells me that none of the above boundary value problems has negative eigenvalue. This means that if lambda becomes negative, then you can't have non-trivial solutions, no matter what the boundary conditions are. And because it is obvious now, because when you take lambda to be negative, okay, then the differential equation's auxiliary equation is going to have real roots, which means you're going to get two linearly independent exponential functions which are never 0. Correct? So you are forced to take the values of the arbitrary constants to be zeros, and therefore your lambda can't be negative, at least for following boundary problems, boundary value problems. Okay, you can verify this for yourself by following the procedure which we did for y double prime plus y equal to 0. This is the standard solution. Only difference will be you will take c1 cos root lambda x plus c2 sin root lambda x. Okay, all right. So the theorem 1 tells me that boundary conditions 1, 3 and 4, boundary conditions 1, 3 and 4, they do not have lambda equal to 0 as an eigenvalue. You can check this for yourself. And the boundary conditions 2 and 5, okay, y dash of 0 equal to 0, y dash of l equal to 0 second, and the periodic boundary conditions, these do have 0 to be an eigenvalue, You know that if lambda is 0, then this will give you the linear solution. Y will be equal to C1x plus C2. Okay. So these do have lambda equal to 0 as an eigenvalue and lambda y equal to 1 as an associated eigenfunction. So it will be a constant eigenfunction, not variable. It should be equal to 1. Okay, so lambda equal to 0 is a situation in which your boundary value problem possesses infinitely many solutions, or at least non-trivial solutions, and due to linearity that will be taken forward. Okay, so let me repeat what the theorem 1 is telling you. Given the differential equation y double prime plus lambda y equal to 0 and any one of these 5 boundary conditions, we are looking for those values of lambda for which the problem has non-trivial solutions. Okay, so the first theorem tells me that none of these have negative eigenvalue, Conditions 2 and 5, both derivatives 0 and the periodic boundary conditions, these have lambda equal to 0 as an eigenvalue and the corresponding eigenfunction is a constant function equal to 1, and 1, 3 and 4 they don't have lambda equal to 0 as an eigenvalue. Okay, so now we will talk about positive eigenvalues, because none of them has negative eigenvalue. Some of them do have lambda equal to 0 as an eigenvalue and some of the remaining ones don't have. Okay, so do they have positive eigenvalues? If yes, what are they? That will be answered by the second theorem. Now prepared a table here. You can prove any two for you, any two, okay, because we don't really have time to prove each one of them, but the theorems are very easy to be proved. Okay, so the problem remains the same. We have the differential equation y double prime plus lambda y equal to 0. Okay, and let us suppose we consider the first boundary condition may represent fixed ends, or both things being kept at constant temperature, equal temperature rather, y equal to 0, y of L equal to 0. Okay, so you can show that the eigenvalues here are n squared pi squared upon L squared, where n is a natural number. So there are infinitely many eigenvalues, and the corresponding eigenfunctions are of the form sine n pi x upon L. There is no cosine term here for fixed ends. Okay, when you go to second boundary condition, that is y dash of 0 equal to 0 and y dash of L equal to 0, remember it does have eigenvalue 1, lambda naught, let's call it lambda naught equal to 1, but it also has non-zero eigenvalues given by the same formula, n squared pi squared by L squared, but this time the eigenfunctions are different, which are cos n pi x upon L for every natural number n. Okay, second thing, I mean this is basically the same thing. Okay, and if you know the eigenvalue, then you can immediately guess what the inside of the trigonometric function is. Okay, but let me also write y naught here. Y naught is equal to 1. Okay, alright. Boundary condition number 3, pi of 0, 0, y dash of L equal to 0. For this, you don't have 0 as an eigenvalue. Oh, sorry, should have written 0 here. 0 eigenvalue. Okay, this one has and the fifth one has. Okay. So if you have boundary conditions y of 0 equal to 0 and y dash of L equal to 0, then your lambda n's or your eigenvalues turn out to be 2n minus 1 squared L squared pi squared upon 4L squared, and the corresponding eigenfunctions are sine of 2n minus 1 pi x divided by 2L. So it is still root lambda x, but what root lambda is or what lambda is depends on what the boundary conditions are. Okay, similarly you can have fourth one, which basically has the same eigenvalues as that of third, but here it is cosine and not sine. Okay, and this is only because of the way you are setting the boundary conditions. Okay. Last, periodic boundary conditions. So in this case, you do have 0 to be an eigenvalue, and the corresponding eigenfunction is y not equal to 1. But you can also have other eigenfunctions corresponding to the eigenvalues n squared pi squared upon lambda squared. And in this case, one eigenvalue, every non-zero eigenvalue has two linearly independent eigenfunctions. First one is cos of n pi x upon l, and the second one is sin of n pi x upon l. And now you can see where is this heading to. This is heading towards Fourier series. Okay, because this being a linear differential equation that we are solving, you can have superposition principle being applied, okay, and that will give you the Fourier series basically of the function that you're going to solve, that you're going to find. Okay, so to summarize, what is a boundary value problem? A boundary value problem is any differential equation. I mean, in the context of second order differential equation, any boundary value problem with a second order differential equation involves giving you the values of either y or y prime at two different locations. So here we just took the first kind, y of 0 and y of l, and also have other boundary conditions. Okay, so that is a boundary value problem. So what is an eigenvalue problem? That discussion began by observing that depending on what boundary conditions you write, the system can either have no particular solution, a unique particular solution, or infinitely many particular solutions, depending on the boundary conditions. So the next question that we posed ourselves was, if our differential equation is y double prime plus lambda y equal to 0 with two boundary conditions, when does the differential equation have a non-trivial solution? It has a non-trivial solution for those values of lambda which we call the eigenvalues, and the corresponding functions are called as eigenfunctions. Okay, very much like eigenvectors, eigenfunctions. Okay, and if we continue that discussion further by considering 5 of these boundary conditions, then we'll get certain theorems or certain standard results. The first theorem tells us that none of them has a negative eigenvalue. Okay, and those two boundary conditions, the periodic boundary condition and the second one, derivatives being 0 at both ends, these do have 0 as their eigenvalue, and the corresponding eigenfunction is y not equal to 1, and the rest of the 5, which are 3 of them, they don't have 0 as an eigenvalue. Okay, and the second theorem told us that these things do have infinitely many positive eigenvalues. Okay, most of them have pi squared in the numerator and l squared in the denominator. That is now by design and the way derivatives of sine and cos work. And the corresponding eigenfunctions, these are also circular functions. Okay, nowhere here we are saying something else is making its appearance except sine cos. Okay, but the reason why you don't take cos here or sine there, or the reason why you have sine of 2n minus 1 pi x and not n pi x, or 2n pi x by 2l, that will be answered by the boundary conditions. Okay, so you can remember this table, you can try any one of them, you write it down for yourself, apply the boundary conditions, see the equations that you're going to get, and I mean, they will be essentially based on the properties of sine and cosine functions. When is sine 0, when is cos 0, and so on. Okay, so try these. This table is important. Any one of these conditions can come in your paper. They will ask you to determine the eigenfunctions corresponding to some eigenvalue. Okay, if you have time during the paper, you can derive, or if you have a strong photogenic memory, then you can remember these results. Okay.